Hello everyone and welcome to today's lecture. My name is Ellie and I'm going to be taking us through our physics revision lecture today. So our lecture is provided by ATAR Notes, who provide resources for high school students, and those resources include study notes, lectures, discussions, videos, newsletters, the infamous ATAR calculator articles, and heaps more. So we're going to be going through a revision of the physics content so far. Alright, we have a 2-hour recorded lecture. There's a live chat, so feel free to ask any questions about the content, studying, or uni. And the content we're going to be going over today is on special relativity and quantum theory and the standard model. Alright, so we're going to be going over a brief revision of that content. Okay, so let's go through the goals of today's lectures. Most schools will be finishing up Unit 4 content by now and will be heading towards mocks, or hopefully you have already done mocks. We'll be revising the Unit 4 content and preparing for mocks and externals. We'll go as in-depth as time allows, so make sure you have something to take notes with. And we'll go over a few worked examples and any tips that I have for particular content, things to look out for, common mistakes, common exam questions, stuff like that. I've been where you are, so I know the pain. I've had a bunch of student stories too, so I really do know a lot about this topic. So just a bit about me before we get started. I graduated in 2021 with an ATAR of 99.55. I'm currently studying law and economics at UQ. I'm living in Brisbane, and physics was one of my favorite subjects. I really loved physics. I really like maths, but the conceptual side of physics was just really cool, honestly. I mean, sometimes it kind of tests you, not gonna lie, especially getting into electromagnetism, which I know you guys would have been well aware of. So some of it probably wasn't my favorite, but especially the content we're going through today, special relativity was really, really cool. So I'm really excited to take you guys through the content today. So let's get started on special relativity, and I'll show you guys just a brief screenshot of the syllabus. So this is everything that you can be expected to know on your syllabus. So the first thing that we're going to start with is muons. Now, before we move on, what I'd recommend you doing if you haven't already is make sure that you make your notes according to the syllabus, just because remember the syllabus contains everything that you need to know. So using the syllabus to study is good to make sure that A, you're not studying anything that you don't need to. Obviously, you don't want to be studying things that you don't need to, because that's just it's not a good use of your time, unless of course you're interested in it, but purely for getting a good grade. You don't want to study things that aren't on the syllabus because they're just not allowed to come up on an external. And secondly, it makes sure that you haven't forgotten anything. Alright, because the number of times I've heard from students that, oh no, I completely forgot about this particular dot point or this particular thing, and it's really sad to hear. So make sure that you go through the whole syllabus and make sure that you understand every single dot point. Alright, let's get on to muons. So, what is the deal with muons? Essentially, alright, muons are these very, very small particles that travel very, very fast. So, they're created in the atmosphere of the Earth, alright? And they have a very, very short lifetime, about 2.196 microseconds. So, Newtonian physics, which is the physics that Newton talked about and invented, would predict that muons really won't come that far to the surface of the Earth. Right? They have such a short lifespan, even though they travel so fast, they're only going to get 8.41 kilometers above the surface. But we actually detect a heap of muons on the surface of the Earth, about 22.8 times more than predicted. So, The takeaway about muons, and this is what you will be expected to know for an exam when you're explaining the muon situation, is that more muons than Newtonian physics predicted were detected on the surface of the Earth. And this suggests the effects of special relativity, which Einstein talks about, such as length contraction, time dilation. And we'll get into an explanation of those in a second if you're a bit rusty on those phrases. But that's essentially what you need to know. You don't need to know all these stats or anything about 22.8, 99.97, yada, yada, yada. You don't need to know any of that. All right, you just need to know the basic concept. All right, moving on to reference frames. So reference frames is something that you need to be able to define, and that's in the syllabus. You need to be able to define what is a reference frame. So, very simply, a reference frame is basically just how something can be observed. So, an observer has a reference frame, all right? Almost anything can be a reference frame. A bug could have a reference frame. It's just anything in which something can be observed, all right? And how the syllabus defines it, how QCEE defines it, is an abstract coordinate system and a set of physical reference points defined by the observer used for the observation and description, or in other words, just maths and calculations, of physical phenomena. So that is the definition that you'll need to remember. So it's basically just like, coordinate system, which is just like a point in space and time, defined by an observer. Alright? So, some consequences of this is that we only measure motion relative to the observer, and the meaning of that is that there is no absolute reference frame. Alright? Nothing is kind of absolutely still. As soon as you kind of think that something is absolutely still, as soon as you think about it a little bit harder, it won't be. You think, well, the house that I'm sitting in is completely still. No, it's not, because it's moving along with the Earth. The Earth isn't completely still because it's rotating and then moving around the sun. The sun isn't completely still because it's rotating around a black hole. It goes on and on. So we don't actually have any absolute reference frame. So there's never going to be like a correct reference frame. All right. The other thing that you need to know is the difference between a relativistic reference frame and relativistic motion. So, relativistic motion or a relativistic frame of reference is one that is not accelerating. Not that it's not moving, it's not accelerating. All right? It can be moving as long as it's going at a constant velocity. All right? So, you could be driving down the road at 100 km per hour and have a relativistic frame because you're not accelerating. You're just constantly going at 100 km per hour in a straight line. All right? So that's something that you need to remember because that becomes really important when we're getting into the concepts associated with special relativity. So, next we're going to have a look at Einstein's postulates. So, Einstein proposed two postulates, and these are important to remember because I have seen exam questions where they just ask you what were Einstein's postulates. So something that is helpful to do is actually just go down to the QCEE syllabus, Control F the document or Command F the document, and I've snipped it down below as you can see, but have a look at the definition on the QCEE website and memorize that one because that is the one that they want you to say in an exam, and you don't need to say any more than that. Don't say any less, but you don't need to say any more. So you don't need to remember anything too complicated, anything like that, alright? So, the first one is that the laws of physics are the same in all reference frames, in all inertial reference frames. Alright? So, what this is saying is that in all reference frames that are not accelerating, and that's an inertial reference frame, it's not accelerating, in all reference frames that are not accelerating, the laws of physics are the same. Nothing changes depending on the speed that you're going. The next one is kind of a knock-on effect of the first one, but the second one is the one you will be dealing with the most, honestly. And that is, laws of physics are the same. As a consequence, the speed of light is c, independent of the relative motion of the source. So the speed of light c, or in a vacuum, is the same in all inertial reference frames. The reason that in a vacuum is stated down here is because the speed of light actually slows down if it's not in a vacuum. Alright, so think about, I guess, maybe sunlight streaming through your window. That window, when the light is going through there, it will slow down the light. Alright? It will slow it down. Similarly, when it's just moving through the atmosphere, the air slows the light down. So light is in its fastest form when it's in a vacuum. Alright, you don't need to know about proof, I don't think. But just in case you want to be a little bit extra prepared, you can remember that it was shown by the Michelson and Morley's experiment in 1887. Alright, so now we're going to get onto the concept of simultaneity. So, events are considered simultaneous if they occur at the same time. Right, that makes sense. That's basically what the definition of simultaneous is. However, when we're getting into more of a special relativity context, this can be a little bit more difficult to determine. So firstly, if two events are occurring at distances from each other and the observer, and especially if those distances are different, it's a little bit hard to determine. So the definition that you need to memorize for simultaneity is on that third dot point. Alright, we can say that two events are simultaneous if light signals from the event, and by light signals we kind of just mean like if the person can see them, right? Light signals, that's what you see the light signals, reach an observer who is midway between them at the same time. So, a common example of this is if you have two lightning strikes at night. If a person stands directly in the middle of those lightning strikes, and if they see the lightning at the same time, then those two lightning strikes are simultaneous. Alright? We're not talking about the sound. It doesn't matter if the observer hears them at different times. It's just about whether they see them. And the observer needs to be standing in the middle of those two events happening. Alright? But if the observer was standing, like right next to one of the lightning bolts and really far away from another one, and he goes, oh, I saw them at the same time, that doesn't mean they're simultaneous, obviously, because he's right next to one of the other ones. Alright. Now let's get on to, I guess, an application of this. So this is the train car example. And this actually touches on one of the one of the paradoxes. Sorry about that. One of Einstein's paradoxes, which we look at a little bit later on. So, if you've already learnt the content, which hopefully you have, remember Einstein has three paradoxes. The lights in the carriage, the barn one, and then the twins paradox. So, this light on the train carriage paradox is one that's touched on by Einstein. But let's have a look at it here. Say we have a carriage which is stationary here, and we have light originating from the middle and then going out, and as you can see, it hits the end of the carriage at the same time. When it hits the end of the carriage, then the doors at either end of the carriage open. And the question is, are the doors opening simultaneous? Here, they are, all right, because measured from the center of the carriage, the light signals from the event occur at the same time. All right, now let's get on to the speed of light. So, the speed of light in a vacuum is a universal constant. Remember, that's linking back to Einstein's second law. And further, we know that nothing with mass can travel faster than it. So this is getting onto the universal speed limit, which is what it's kind of colloquially called. The speed limit. So nothing with mass can actually travel at the speed of light or faster than the speed of light. All right, so we generally simplify the speed of light to 3 times 10 to the 8 meters per second. I believe that's in your formula sheet too. Don't bother with the 2.998 yada yada yada. You don't need to worry about that. So there is an unusual phenomena that occurs when an object with mass approaches the speed of light. Okay, and this explains why nothing with mass can travel at or faster than the speed of light. So, these unusual phenomena include time dilation, length contraction, the relationship between mass and velocity, and we'll have a look through those. So, the key takeaway from this slide is that nothing with mass can travel at or faster than the speed of light, and the reason for that is those 3 concepts that we'll have a look at in a second. So, a suggestion is to make sure that you add the following terms to your glossary or to your flashcards if you don't already have them, and I primarily say this because on your syllabus it asks you explicitly to define these concepts. Alright, so now we're going to go over what these concepts are and how they relate. So, the first one is the mass effect. So, if you guys remember from maybe year 9, year 10, something like that, Newton's second law, F equals ma, right? So, Newton's second law suggests that as long as there is an unbalanced force, that an object will continue to accelerate. Alright? An object will continue to move unless acted on by an external unbalanced force. So it kind of predicts a very linear relationship, the more force you put in, the more an object will accelerate. If you put lots of force, it will accelerate a lot, little bit of force, little bit of acceleration, that kind of thing. However, when we get into the relativistic scene where we have things moving really, really fast, we know that this is actually not true. F equals ma is still true, but we know that Newton's second law is not true. However, we know that Newton's second law is not true because what we observe is that as we try to accelerate an object closer and closer to the speed of light, its mass will increase too. And we'll go over more of this in a second. So, we know that mass is an intrinsic property, but it's also a relativistic property. So mass will also change depending on the speed of the object and the frame of reference. So we have 2 values you need to remember, and it's important to remember the distinction between these, m naught and m, because it's easy to mix them up. M naught is the rest mass, and this one is kind of the one that stays the same, alright, or the invariant mass. It's always going to be the lighter one. M naught is always going to be smaller than m. So m is the relativistic mass, and this is the one, sorry, my mistake, other way around. So m is the relativistic mass, and this is the mass in the frame at which the object is moving at a velocity v. So think about it like this. If you have a particle whizzing around a room, and there is, like a scientist watching the particle, they would be seeing m, relativistic mass, because that's the mass in the frame at which the object is moving. All right, they see the object moving. M naught will be the mass of the particle if there was a tiny, tiny man standing on top of the particle and watching it, and holding onto it, because that is the frame in which the particle isn't moving. That man does not see the particle moving, he sees the room moving. So the tiny man on top of the particle would measure the rest mass, and then the scientist observing would measure the relativistic mass. So m naught is always going to be smaller than m. Alright, this is the formula that you need to be aware of for determining the mass effect, and this one is in your formula sheet. So as you can see, the relativistic mass is always greater than the invariant mass, which is what I said before. And the relationship of mass increases as velocity approaches the speed of light is exponential. So it's not linear like Newton predicted, it's exponential. And I'll show you guys what that looks like. So, as you can see, when the speed is very, very small or close to zero, the mass is 1. As the speed increases, and particularly just about by the time we hit a half, it really starts to increase. The mass increases exponentially. The point where, as you can see, where we're getting to C, this line C here, the mass is almost getting vertical. So it's approaching infinity. So as you might be able to see, this is why our objects with mass can actually never achieve that speed of light. And that's because the closer and closer they get to the speed of light, the more and more mass they have. Alright? So think about this as more of a knock-on effect too. If an object has more and more mass, it requires more and more effort to accelerate it. If you're trying to push a really big object, it requires a lot more force than a really small one. So you kind of need more and more energy to actually accelerate this object. And what's actually happening is that energy that you're putting in to accelerating that object is actually going into increasing its mass. So you're putting more and more energy in up here, but all of that energy essentially is just going to making it bigger, right? So the issue is we can never accelerate a mass with infinite mass because we don't have infinite energy to do that with. Alright? So, now let's get on to the next effect, and this is time dilation. So, time dilation is probably the most famous effect that you would have heard of. I know it's the one that I heard of before I got into year 12. And this is kind of the more time travel-esque one. So this is the cause of the moving clocks run slow phenomena. So, time is relativistic. And what that means is that the interval between two events cannot be the same for two observers that are in motion with respect to one another. So as long as you have two inertial observers, one's not accelerating, they're moving with respect to each other, the time that they measured will not be the same. So, there's a few different explanations that you can think about for this. But the explanation that makes the most sense for me goes a little bit like this. Say you are having you have two particles, all right, and they are moving along at very, very close to light speed. So, we know that the speed of light, c, is constant in a vacuum. Alright? So, if we have an observer seeing our particles moving along, because it's so close to the speed of light, all right, he's going to be seeing them move close to the speed of light, regardless of what he's doing. Okay? But those particles, if they were observed by an observer also going close to the speed of light, he would have to see those particles also going close to the speed of light, right? So, if we have an observer going at 80% the speed of light and he sees particles going at 90% the speed of light, he has to see them going still very close to the speed of light. Okay? So the complication arises there, and what it kind of comes down to is the fact that things that are traveling at or close to the speed of light need to travel a greater distance in a shorter amount of time to kind of compensate for Einstein's second postulate, all right? Because if two observers are seeing those particles and they're seeing them go at pretty much the same speed, all right, something needs to happen to make up for that. So it only makes sense that the particles kind of need more time in their perspective to move, and the distance that they have to travel also kind of has to get shorter in their perspective to move. So have a think about it in terms of our equation for velocity equals distance on time, right? If we're just thinking about a beam of light now, if the velocity of the beam of light always has to be the same, then the distance and the time are the things that have to change. So we'll get into more of that later on as well when we're explaining some more of the paradoxes, but that is the essentiality of it, all right? Because the velocity has to stay the same, the distance and the time will change. So let's get into the formula that you need to know. So we have T equals T naught over root 1 minus V squared over C squared. So, T naught is the proper time and T is the relativistic time. So T naught is the time that you would measure if you were the thing in which, if you had the observation or the relative, the reference frame in which the object wasn't moving. So if you were on the rocket, and then the relativistic frame is the one in which, or T, is the one in which you're seeing that rocket move. All right? So, the time dilation is maximal when the velocity is equal to c. So when something travels at speed c, it actually does not experience any time at all. So we know that light actually doesn't experience any time. So, kind of as you get closer and closer to the speed of light, time slows down. And I just want to make an important clarification here. I'm not saying that you experience things yourself in slow motion. Alright? It's more so that people watching you would think that you were experiencing things in slow motion. Okay? So, let's get on to length contraction. So, consider the astronaut rocket ship example again. So, the elapsed time in the rocket is T naught, and the elapsed time on Earth is T. So the velocity is considered to be consistent for both frames of reference. Thus, in order for this to be possible, the length traveled must be different for the two observers. So we have L naught, which is the proper length, the length of those on Earth not moving in the stationary reference frame, and L, which is the length for those in the moving frame of reference. All right. So as you can see here, we have a quick table of which values apply for which frames of reference. So it can be a little bit confusing, and that is why it's important that you remember these, alright? So it's important that you know the differences between them, and make sure when you're practicing questions involving all of these formulas that you're checking your answers to make sure that you're consistently applying the right values. Okay, let's get into some more of length contraction. So, in summary, the relationship between velocity, length contraction, and time dilation is summarized right here. Alright, and this is how you can determine the velocity of an object moving. One thing you also need to keep in mind is that when we're talking about length contraction, the length only contracts in the direction of motion. Alright, so having a look at our circle here, the height of the circle is not changing. It's only the width of the circle. Alright? So, the length only contracts in the direction of motion. Say you're driving past, on the road, you're driving past a suburb of houses. You're driving close to the speed of light, so you see the length contract. Right? So, you see those houses as skinnier, but you do not see them as taller. Alright? It's not like you're seeing things being squished out. You're just seeing them being skinnier, but not taller. The height is the same. You're seeing them as skinnier. And the reason for that is because you're only going horizontally. If you were going vertically, say you were in a rocket in a suburb of houses, and you blast off, then you would see the width not change, but you'd see them get very short. Alright? So the length only contracts in the direction of motion. So, this formula is what we use to determine the relativistic length. So, as you can see, it's fairly similar to the ones we've been going over so far. And you can just apply that one to find the relativistic length or the proper length for a question. Now getting on to light as the universal speed limit. So, it should now be pretty clear why nothing in the universe with mass can travel at or faster than the speed of light. So, as we know, as an object approaches the speed of light, its mass approaches infinity, its length approaches zero, and the elapsed time for a given period approaches zero. Alrighty, now we're going to get onto mass-energy equivalence. So, anything with mass has an equivalent amount of energy, right? So anything with energy has an equivalent amount of mass. So, the conversion that we use is E equals mc squared, and this tells us about how much energy is contained within a certain amount of mass. Alright? So, of course, E is the energy, m is the mass in kilograms, and c is the speed of light, which is 3 times 10 to the 8. So, The primary consequence of this relationship is that an object at rest has intrinsic energy that corresponds to its rest mass. All right? So when the object is in motion, in other words, when it has kinetic energy, its relativistic mass is greater than its invariant mass. Okay, what you'll typically be asked in relation to externals is you'll be asked to find how much energy is in a certain amount of mass, or vice versa. All right. This formula, though, does have application in a few different contexts, so make sure that you are keeping it in the back of your mind for other types of questions. All right. Now let's get into the twins paradox. So the three paradoxes are things that you need to make sure that you understand, because something on the syllabus says that you need to be able to explain each of these three paradoxes. Now, for a little bit of background, Einstein came up with these three paradoxes when he was conceptualizing special relativity. So, he came up with the paradoxes kind of to explain his theory and really hit on those contentious points that sometimes people would try to argue. So, the twins paradox is probably the most famous one. It's probably the one you guys have heard of the most. And the setup goes like this. We have two identical twins, one of which makes a journey into space at a high speed. All right. Upon returning, he notices that the twin on Earth has aged more. So he goes on his fast journey, he comes back, and his twin looks older. So, consider an application of inertial reference frames and time dilation. Each twin has observed the other in motion, alright? So, they should have found out that the other had aged less or was younger, but this is not so. So thinking about the relativistic motion and the inertial reference frames, each of the twins see the other one moving really fast, right? So the twin on the rocket looks back and sees the twin moving away from him on Earth really fast. And the twin on Earth sees the twin on the rocket moving away really fast. All right? And what we've gone through so far is that when you see something moving, at high speeds, you're going to see that thing experience less time. All right? You're going to look on, so the person on Earth is going to look on in the rocket and see that the person on the rocket is experiencing things in slow motion. Right? That's what they see. Whereas the person on the rocket is going to look back on Earth, and this is what we've learned so far, would look back and see that the person on Earth is moving in slow motion. So the real question is, how can we reconcile these two? Alright? Why is it that the twin who comes back on the rocket sees that the twin on Earth has aged more, alright, when this doesn't really seem to match up with what we've learned so far? So, if you guys haven't heard of the twins paradox before, or if you have and you're just studying, make sure you pause the recording and have a quick explanation to yourself, have a think about it, write it down. What is the solution to the twins paradox? Alright? I want you guys to have a think about, as a hint, pause the recording now if you don't want a hint. As a hint though, have a think about what is a necessary requirement for the content that we've learned. Go back to the first few slides that we went through. What was a necessary requirement? We had our reference frames, but what was necessary about those reference frames? Alright, I'll go to the answer now. So, the key is that only one twin spent the entire time in an inertial reference frame. So one of the twins was on Earth in an inertial reference frame, but one of the twins accelerated away from the Earth on a rocket. Accelerated, remember, an inertial reference frame is one in which there is no acceleration. So the twin on the rocket accelerates away. He then gets to the planet and accelerates by turning around. Remember, even if you maintain a constant speed, if you change direction, that also constitutes as changing velocity and accelerating. And then coming back and then slowing down to land on Earth. So, Einstein's theory deals with constant motion only. Special relativity does not encompass accelerated frames of reference. So this is why this happens. Alright? So, the essential breakdown, and this is, remember, what you need to be writing on your external, because you only have a little bit of time to explain this. You're going to want to do it in a few lines max. So what you'll want to do is write this concept down in your own words, alright, and then memorize it, and then take that into the exam. And the lines along which you want to memorize is one twin goes out in space on a fast rocket, while one twin remains on Earth. And then the paradox is, since they're both moving relative to each other, which one will age faster and which one will age slower? Alright, and then the solution is that the twin in the rocket did not have an inertial reference frame because he accelerated upon leaving the planet and then turning around and then coming back. So Einstein's theory does not apply. Alright, let's move on to the next paradox, which is the flashlights on a train paradox. So this is the one that we briefly touched on a little bit before. So we have a person on a train in constant motion with a torch. He shines the torch at a mirror on the other side of the carriage, and then the distance that the light beam travels from a frame of reference of someone on an embankment watching the train go by, the light travels a shorter distance. So, let's have a think about this. We have a person on a train. The train is going very fast, but it's going at a constant speed. He's shining a light on a mirror on the other side of the carriage. Alright. And the light beam is traveling between him and the mirror. However, a person on an embankment watches the train go by and sees that the light travels a shorter distance. Alright? How is this possible, knowing that the light cannot travel faster than c? Now, there are a few different variations on this paradox. So, before I get to the solution, I might just quickly explain one other variation that I think is a little bit more common than this one. Alright? So if you are a little bit confused with this one, then don't worry. So the one that I've seen that's a little bit more common is where you have, again, a train carriage moving by, and then you have a lamp in the center of the train carriage. And the lamp is turned on, and the light, spreads out and goes to either end of the carriage. Somebody who is on the carriage standing next to the light, what they would see is, for our carriage, with our light, sorry, I will redo that. That was terrible. our carriage, the light, they would see the light hitting either end of the carriage at the same time. This is a person standing on the train. Alright? But if we have a person standing outside of the train, what are they going to see? They're going to see the light in the middle. Alright. What else are they going to see though? The train is moving at close to C. Alright. So the light coming out of this end of the lamp is kind of almost chasing this end of the carriage because the carriage is moving away so fast, it's almost as fast as the light itself. Alright? So this side of the light is almost chasing the carriage because that side of the carriage is moving so fast. But the light here gets to this side of the carriage a lot quicker. And that's because this end of the carriage is almost moving up to meet the lamp. Alright? Sorry, to meet the light. Because that end of the carriage is again moving so fast, so close to light. Right? So this is what a person on the embankment would see. So, what you can tell is that for a person inside the train, the light hitting the either end of the carriage doors is simultaneous. But for a person standing on the embankment, the light hitting either end of the carriage is not simultaneous because the light hits the back end of the carriage before it hits the front end of the carriage. Because the back end is like moving up to meet the light because the train is moving, and then the front end is like moving away from the light. Alright? So, the real question is, how can we explain, right? How can something be simultaneous here and not simultaneous here? So, the key is that events simultaneous to one viewer are not simultaneous to another. So the distance that the light had to travel depends on your reference frame, right? So it doesn't matter that in these two viewpoints, the light hitting either end of the carriage is not simultaneous. That doesn't matter, alright? Two events can be simultaneous in one frame and not simultaneous in another frame, and that is okay. Alright. Now let's hop into the last paradox, which is the ladders in the barn paradox. So, for this one here, we have a ladder or a pole which is parallel to the ground, right? And typically we have somebody running who is holding that pole and running, holding it horizontally. Alright? Kind of like one of those, I can't remember what it's called. The sport where people hold the long sticks and then jump up on them. If you know what I'm talking about. If you don't worry. So we have a runner holding the ladder or the pole horizontally to the ground. So, what happens next is the runner runs through a barn. Alright? She runs through a barn. Now, before this was all happening, alright, she laid out the ladder next to the barn, and she saw that the ladder was actually longer than the barn. Alright? So the ladder is, say, twice the length of the barn. And that's what she did. So she tested it all out. She laid the ladder next to the barn. She saw that the ladder was twice the length of the barn. Now she's running at a very, very fast speed towards the barn. Okay? She runs in, and from her perspective, alright, the barn got shorter. Oh, sorry, skinnier. not shorter, because its length contracted. So the barn got skinnier. All right. So she's running through the barn, and the barn is even skinnier than it was before, meaning that the ladder fits even less than it did when she measured it initially. All right. So she's running through, and this ladder is way too long for the barn. She keeps running. All right. Now, we also have a farmer who is standing next to the barn, and he's watching what's happening. When he sees the runner run into the barn, he sees the runner's length contract. All right. So the ladder gets skinnier. In the direction of motion. All right. So from his perspective, she's seeing the runner run in, but because the ladder is so much shorter, she's seeing the farmer is seeing the ladder fit inside the barn. So even though it didn't fit when the runner laid it outside next to the barn, because she's running in now, she's going so fast, the length of the ladder fits inside the barn. All right. And that's from the farmer's perspective. So, what we have so far, we have a ladder, which when the runner measured it before she went for a run, was twice as long as the barn. Now the runner is running, holding the ladder horizontally. She's running really fast. She runs through the barn. From her perspective, the barn is contracting. It's getting really skinny. And she sees that the ladder is like even longer compared to the barn than before. All right. The farmer, standing watching, sees that the ladder is a lot shorter because the runner has contracted in length, and so he sees that the ladder fits inside the barn all at once. So the next complicating factor is that we have two doors on either side of the barn. All right. So the runner is running through the two doorways, and she is seeing two doors on either side of the barn. From her perspective, when she's running through, the doors are not closed at the same time because she can't fit inside the barn. But from the farmer's perspective, he is seeing those two doors close at the same time because the runner can fit inside the barn. So, the paradox is, how can it be that the farmer can see both doors closed with the runner inside, whereas the runner does not see that at all? How can that be? So, what I'd like for you guys to do is to pause the recording if you haven't gone through this yet or you're just a bit rusty. Make sure you have a think about why this could be. Really try to test your memory or just try to think of an explanation. Or if you have studied this and you're more prepared for externals or mocks, make sure that you do a brief explanation of the answer or how you would answer it in an external. Alright? So, I will show you guys the answer. So again, the solution is that simultaneity is relative. Alright? Just because two events are simultaneous as measured from one reference frame, it doesn't mean that they're simultaneous from another. So the doors being opened and closed are not simultaneous events in the frame of reference of the pole or the ladder. Alright? So, when the runner is running with the ladder, what she sees, she's running to the barn, alright? She sees herself run in the back door. Actually, I'll draw a diagram. So she's running in the ladder. Here's the barn. Alright. So when she's running in, this front door is open. All right. She's running in, running in. Then there's a point where both doors are open and she's in the middle. All right. And then there's another point where she's run through most of it. And the back door is open. And that's when she is just running through this last bit here. Alright, so even though the doors are closed from her perspective, they're not closed simultaneously. In fact, the front door is open before the back door, and then after a while, the back door is closed and the front door is closed and the back door is open again. Alright? Okay. So the solution to this one is that the events of the doors closing are not simultaneous, and that is okay. Let's move on now to our next topic for today. So now we're going to be going through quantum, alright? Quantum theory. And as you can see here, these are the syllabus stop points on everything you need to understand for quantum theory. So, the first thing that we're going to look at is Young's double slit experiment. Now, as a bit of revision, remember, quantum theory is, we look a lot at the wave-particle duality of light. Look at the experiments supporting the wave model or the particle model, because light can act as either a particle or a wave. Right? So, we have a look at that. Then we also have a look at the different models of the atom. So the Rutherford and Bohr model, primarily, and the features of those, the difference of those, and then the weaknesses of particularly the Rutherford model. Right? And those are kind of the two main things that we focus on in this topic. So, Young's double slit experiment. Essentially, what happened is our scientist named Young, he got a sheet of material and he cut two slits in the sheet. Alright, that's what you can see here. Two slits in the sheet. And he shone light through. Okay? And he observed something on the other side which was shocking at the time. So, let's have a look. Up here we have what he would have seen if light behaved as a particle, and down here we have what he would have seen if light behaved as a wave. So, up here we have our two slits, our little particles of light coming through, and then as you can see, they've just kind of fallen right behind those two slits. That kind of makes sense, right? Say you're throwing like paintballs or water bombs or something through two slits, they're just going to kind of fall directly behind those two slits. There's not going to be too much variance there. Alright? Now we can see is what would happen if light behaved as a wave. So, we have our wave coming in, and because of our interference patterns with waves, we have our constructive and destructive interference pattern with waves. What we actually see is them crossing over like this to create a pattern. And this is more so what you would have seen if you had had some water. So say you have water with two slits and you create a wave of water to go through those two slits. This is what you would expect to see. You'd expect to see the water bend around these two slits like this and then kind of create little, I almost want to say like dimples of water. If you have seen that kind of thing, alright, if you kind of create two splashes almost in the water with your hands, if you even just go do it now in your bathroom sink or something, what you'll see is that where those two waves collide, they create big spots and little spots, alright, and then flat spots. So what we call this, and you might be familiar with this from year 11, is constructive and destructive interference. So where the two waves meet and they're already high, they're going to create an even higher one. Where they meet and they're already low, they're going to create a lower wave. And where they meet and one's high and one's low, they're going to like cancel each other out and become flat, right? So you don't need to know too much of the background behind this. It's just useful in understanding the concept. So as you can see, we have our constructive and destructive interference patterns, and then what we see on the board back here, all right, is a higher concentration of light in the center here. And if you have a look at this blue line, that's because this is where all of this constructive interference is happening. But on these ones, all right, we're kind of getting fainter and fainter. So this one is going to be pretty weak. We're not going to have a lot of light here. This one's going to be pretty strong. This one's going to be moderately strong, and so forth. All right. So this is actually what you can see. So you see we have this big bright spot, dark, dark, littler, littler, and then dark moving out from there. So this is what Young observed. So what you need to remember for an external on this topic, all right, is you need to remember kind of a brief explanation of why Young's double slit experiment showed that light could behave as a wave. All you need to remember is that the light shone through the two slits created a constructive and destructive interference pattern, which is a property of a wave, and thus created a pattern behind that, which was more intense in the middle, and then created decreasingly bright spots farther and farther out. Whereas if light had behaved as a particle, you would have just seen two big splotches behind there. Alright, so this is how Young's double slit experiment showed that light could behave as a wave. Now let's get into what light actually looks like as a wave, alright? So, these are the characteristics of electromagnetic radiation. So, it creates consists of oscillating electric and magnetic fields. So those red waves are electric fields, and those blue waves are the magnetic fields. So as you can see, they are oscillating, right? They're going back and forth like this. And they're also perpendicular to each other. So they're at right angles to each other, all right? The other thing you might notice is that the direction of those two waves is perpendicular to the direction of propagation. So our two waves are going up and down and side to side, but the direction is going this way, right? Or this way for you guys, okay? So the oscillating electric and magnetic fields are at right angles to each other and right angles to the direction of propagation. So the speed of the wave is dependent on the magnetic and electric properties that it is traveling in. All right? So an example of this is that the speed of light differs in different substances, the refractive index. So say you have electromagnetic radiation traveling through a pane of glass. All right, that's going to slow it down. So if you have light traveling through water, that's also going to slow it down. But if you have light traveling through a vacuum, that is the fastest that it will ever be. So you can calculate the energy of the light using E equals hf, where E is the energy in joules, h is Planck's constant, and f is the frequency of the light. All right? So, as a recap, the characteristics of electromagnetic radiation are that it consists of oscillating electric and magnetic fields which are at right angles to each other and the direction of propagation. All right. something that I would expect to see in an exam on this is more so just a question asking you to describe the properties of electromagnetic radiation. And they'll just mix up, which things are perpendicular, which fields are oscillating, that kind of thing. Or alternatively, you might even be asked to identify which diagram correctly describes electromagnetic radiation. So I'll give you like a few diagrams that look like this, but they'll all be slightly different, and 3 out of 4 of them will be wrong. All right, it's not something that you need to know a bunch on. Okay, now let's get on to black body radiation. So, black body radiation is an experiment that was done that showed that light behaved as a particle. Alright? So far we've gone through Young's double slit experiment, which showed that light behaved as a wave. Now we're going through black body radiation, and this showed that light behaved as a particle. Later on, we're going to go through the photoelectric effect, and that showed that light behaved as a particle as well. So, let's go through the concept of black body radiation. A few hundred years ago, experiments were being performed on completely black metal objects, and we call these black bodies. So a black body is a completely black object, and theoretically it does not reflect any light. It only absorbs the light that's being shone at it, right? Because it's black and it's metal, so it's a good conductor, that kind of thing. We don't actually have any perfect black bodies. Alright, so none of our black bodies would actually be perfect, because a lot of them will still, or all of them actually, would still reflect some of the light and not absorb all of it. But we have some that are pretty close. So, essentially what's happening, we have a black body, we're shining light on it, and what's happening is the black body is getting so much energy that it's emitting radiation, alright? And this is done through electromagnetic radiation. So, a really good example of this is a hot plate, if you have one at your home, where it has a wire coiled up underneath where the pan goes, and that wire gets really, really hot, and then it emits red light, and it's emitting the EMR there. So what we have light being shone on this black object that's absorbing most of the light, and then it's emitting light back. So, the interesting part about black body radiation is to do with what frequencies of light are emitted. So remember, the frequency of the light tells us about its color, right? The color of the light. So, as you can see on the graph, we have a graph between the brightness B and the wavelength. Remember, the wavelength and frequency are directly related. So, the brightness is the intensity of the light. It's essentially like how much light is there. Alright, it's not to do with the color, it's to do with how much there is. So, as the brightness increases, what we see for a little bit is that the wavelength increases too. Then there is a peak, and after that, when the brightness is decreasing, the wavelength is still increasing. So, all these different colors of curves correlate to the different temperature of the black body. All right. So obviously the greater the temperature, the more energy is being emitted. So that's that big purple curve that we don't even see the top of. So this is what was observed when these black body radiation experiments were being done. The interesting part about this is that it isn't what other scientists would have expected. So they didn't understand why this is what happened. So why is the brightness why does the brightness and the frequency not increase exponentially? Sorry, why does the brightness not increase exponentially with the temperature? All right, and with the wavelength. So as you can see, we have that peak, but even after the wavelength is increasing, the brightness is still going down. So why does this happen? Why doesn't the brightness just increase with the wavelength? So, it eluded scientists until Max Planck proposed that the energy emitted by black bodies was from the vibration of atoms limited to certain frequencies that were multiple of some value. Alright? So he was saying that these frequencies that the atoms vibrated were multiples of a discrete value. So in this situation, light is emitted as quanta, not as a continuous wave, as discrete little packets. So discrete little packets of light are particles. Alright? The frequency of light emitted by the vibration of an atom is proportional to the change in energy of the atom, related by Planck's constant. Right? So this whole black body experiment proves that light exists as a quanta. And we have below a few equations that might be useful for you. So we have E equals hf, C equals the wavelength multiplied by the frequency. So in your formula sheet, I believe like more so at the top of your formula sheet, you're given that V equals wavelength times frequency. In this situation, because light is being emitted, like the velocity is just c, the speed of light. So if you're looking to remember that formula, that's how you can. Which gives us that E is equal to hc over the wavelength. Alright? So, this is how you can determine the energy of light emitted. Alright. The next important formula that you need to know in relation to this is the maximum wavelength of the curve. So, Wien's displacement law describes the relationship between the temperature and then the peak wavelength of the black body radiation curves. Right, and this is equal to the wavelength is equal to B, which is Wien's displacement constant, divided by the temperature T. So it's important to remember that the temperature is in kelvins. Right? The temperature is in kelvins. It's really, really easy to forget that. Okay? Temperature is in the unit kelvins. How do you convert between degrees and kelvins? All you have to do is add 273. Alright? So the temperature in Celsius or in degrees, alright, will be the temperature in kelvins minus 273. And that is how you can convert between Celsius and Kelvins. So all you have to remember is that 273 number. Alright, something before we get into the next slide that I want to make sure you guys are aware of is something you'll likely be asked on this topic is like, what is the maximum, what is the peak energy? Or what is the peak brightness? Or something like that of the light. So all you need to do is you need to have a look at the maximum wavelength, and then you need to go back to these formulas here, sub that maximum wavelength in, and you'll get the energy. Alright, so these are the equations that it's important for you to know. The energy E is a single quanta of light with frequency F related by Planck's constant H. Remember, Planck's constant is in your formula sheet. The frequency and wavelength of light is related to its velocity c. Remember, this is the one that's in your formula sheet as v equals wavelength times frequency. And then combining those above two equations together, we get this last one, which is an amalgamation of them both. Alright, now let's get on to the photon model of light. So, let's talk about what photons are and how they relate to what people conceive of as the model of light. So, the photon model or particle model of light deals with particle light behavior. Alright, so instead of seeing that light behaves as a wave, we see that light behaves as a particle. Now let's get over the properties of photons. So, photons have no rest energy, alright, we're calling special relativity. They have no mass either. Remember, because going back to special relativity, photons travel at the speed of light. Nothing with mass can travel at or faster than the speed of light. So they don't have any mass. And they also have kinetic energy. Alright? So, the energy of the photon is described by mc squared. Alright, now something you might have noticed is that because our photons don't have mass, this seems to pose a few issues. But we'll get into that a little bit later, and you'll see the explanation of how that all pans out. So, let's get into the photoelectric effect. Now, just to kind of join the topics that we've done together. So we've gone through Young's double slit experiment, we've gone through black body radiation. The photoelectric effect is evidence that light behaved as a particle. Alright, so we kind of have evidence that light behaves as a wave, evidence that light behaves as a particle. Okay, light behaves as a wave, we have Young's double slit experiment. Light behaves as a particle, we have black body radiation and the photoelectric effect. There are a few more experiments, but we don't actually get into them in year 12. Alright, so it's just good to kind of keep in your mind which experiment supports what model of light. So, when a metal surface is illuminated by electromagnetic radiation of a high frequency, electrons are ejected from the metal surface as a photocurrent. So, if we shine a light on a metal surface, it will give a little bit of energy to the surface, and eventually it will give energy to the electrons inside of that surface, and the electrons will jump out. Alright, and they'll create a photocurrent because they'll run around in the wire and create a photocurrent. So we have a few restrictions on this though. The electrons only jump out if the light has a sufficient frequency. We call this F naught. and the ejection frequency differs depending on the metal, right? So some metals you need a lower frequency, some metals you need a higher frequency to get any electrons out, right? So if your frequency is too low, you can be shining the light on the surface of the metal and no electrons will come out. Even if you have a really, really bright light, no electrons will come out. So remember, the frequency of the light is related to the color. The brightness is how intense it is, all right? Like how much light there is there. So, you could have a really bright, like massive, excuse me, really bright, massive torch that, you shine in somebody's eyes and it blinds them because it's so bright. But it doesn't have a high enough frequency, and so no electrons come out of the metal. Alright? In other words, before you've reached your threshold frequency, or the ejection frequency, it doesn't matter how bright the light is, no electrons will come out. However, once there is a photocurrent, once you do have a few electrons coming out, because your frequency is high enough, if you make that light brighter, then a lot more electrons will come out. Alright? So, once you've achieved your threshold frequency, if you increase the brightness, more electrons will come out. The difference is, more electrons are coming out, but the energy of those electrons has not increased. So it doesn't matter what the brightness is, as long as you've reached that threshold frequency and there's electrons coming out, those electrons will all have the same amount of energy, alright, coming out. So, if you increase the frequency of the light, then that will increase the amount of energy that the electrons have. But if you have a really, really high frequency, but a really dim light, only a few electrons will come out. So what I'm getting at is the frequency of the light tells you the energy that the electrons have. The brightness of the light, after you reach a threshold frequency, the brightness of the light tells you how many electrons there are, right? Frequency, how much energy. Brightness, how many. Okay? So, now let's have a look at some of the explanation for this, rather. So, this phenomena cannot be explained by the standard wave model of light, and it supports the particle theory. So let's have a quick think about why this supports the particle theory, alright? So, let's go back to our last slide and see just the properties. So, when we're increasing the frequency of the light, alright, we're increasing the frequency, we're increasing the energy of the light. If light is a particle, high frequency particles, high frequency photons, will have a lot of energy, right? Because we have E equals HF, right? More frequency, the more energy, right? So if we have high frequency photons coming in, they have a lot of energy. They come in to the metal and they give all of their energy to one single electron, right? They give all of their energy to one single electron. And that is why when that electron comes out, it has a lot of energy. The point being, the photon coming in doesn't spread its energy around multiple different electrons and kind of like spread it out. So, more electrons coming out, but they don't have a lot of energy. No. Each photon gives all of its energy to one electron each. So, if you have a low frequency and you're shining a light on the metal, the photons are coming in, they're giving Each of them are giving energy to one electron. All right. But because they're not giving them enough energy, the electrons don't have enough energy to jump out of the metal because they're still inside their atom. All right. They've got a little bit of energy, maybe they jump up away from the nucleus a little bit, but they can't jump fully out of the atom altogether. All right. So once you've reached the threshold frequency, you've got just enough energy to get those electrons out of the metal. And then after you keep increasing the frequency after that, each of those photons keep on giving a greater amount of energy to each of those electrons. Now, if light were a wave, what you'd expect to see is like, instead of just like little packets of energy like you do with particles, it's like a continuous wave. So what you'd expect is even if the frequency is really low, all right, it kind of just keeps on like washing up more and more energy and like building up and distributing it to each of the electrons, all right? So after a while, some of the electrons have enough energy to jump out. But that's not what we see, right? We see at a low frequency, no electrons come out. Not that it takes a while, no electrons coming out. Which means that the energy is not building up, it's been given in discrete packets. Alrighty, now let's have a look at the brightness. So, the brightness of a light corresponds to how many photons there are, right? It makes sense, if something is really bright, it makes sense as there's a lot of light there, there's a lot of photons, alright? So, high intensity, high brightness, we have a lot of photons, which means coming into the metal, there is a lot of photons who can give each electron all of their energy. Alright? So, if you have a really high frequency and a really low intensity, you're shining your light on the metal, alright? And each of your photons have a lot of energy, but there's like only 3 photons. So only 3 high energy electrons will jump out. But if you have a high intensity, you have hundreds and hundreds of photons, then they'll all come in and give their energy to hundreds and hundreds of electrons, and you'll have hundreds and hundreds of electrons jumping out. Right? Do you get the picture? So, this is how the photoelectric effect showed that light behaved as a particle in this instance. Alright? Now let's go over a few of the formulas that you need to be aware of. So, the first one is that the energy of the photon is equal to hf. Alright? Now, the energy of the electron is what we call W, or the work function. Alright? And this is what we call like how much work or how much effort it takes for the electron to jump out of the metal. Alright? Because obviously it's still bound to its atom. We need to give it enough energy for it to jump out. So, this is equal to H times the threshold frequency F naught. So as you can see, this is directly derived from this formula here. Alright. So we have the threshold frequency, which is how much energy it takes to get that electron out. Now, the maximum kinetic energy of the ejected electrons will be however much energy that photon had, minus however much it took to get it out of that metal just to begin with. Alright, so the photon's coming in, it's giving it a lot of energy, it's giving the electron a lot of energy, the electron has to use some of that energy to get out of the atom, and then once it's got out of the atom, it has the remainder of that energy to bounce around, essentially. So, now let's get on to the stopping potential, or the stopping voltage. Alright, so what happens here is if we reverse the direction of the potential, we have a negative potential energy. Then the negative potential will push the electrons in the other way, And eventually this will become large enough to deflect the entire photocone. So you won't have any electrons at all. Alright? So just for a little bit of background, a negative voltage, right, is where you have a negative potential difference. So kind of a way that you could visualize this is when you usually think about your like battery wire setup, all right, but instead here we have our little photocurrent apparatus instead of a battery. What you usually think about is, oh, like there's lots of positive lots of positive protons over here, positive, positive, positive. So, you know, all the electrons over here want to race around to get to the positive charge, right? That's how people tend to think of it. There's a positive charge on the other side, so the electrons want to race around to get there, right? What a negative voltage essentially is instead of having a positive charge there, we have a negative charge. Oh no, my box. We have a negative charge. So we have negative charge over here, which means the electrons, they do not want to go around here, all right? So what we're essentially saying is if there's only a couple electrons over here, then the photocurrent will still come around. But after a point, we'll have so many electrons that nothing will come around from the photocurrent, and the current will be stopped. Alright? Or that is the cutoff voltage. Remember, voltage is like the potential difference around the circuit. So after a certain point, the electrons on the other side will be too much. The negative charge will be too much, and then none of the photocurrent will want to come around. So the kinetic energy of the electrons can also be determined by this, where we have the Q multiplied by the stopping voltage, right? And where Q is the charge. So I just want to quickly get into an important thing that you need to understand about the stopping voltage. So typically you kind of see a graph of the stopping voltage, and you just need to understand like what values actually affect the stopping voltage and what don't. So the brightness of the light being shown on the metal does not affect the stopping voltage. Alright? The brightness does not affect the stopping voltage. Alright? So the frequency affects the stopping voltage. And I want you guys to pause the recording and have a quick think about why that is, alright? Remember, the frequency determines how much energy the electrons have. If the electrons have more energy, they're more willing to go around the circuit even if there's a negative voltage. But if they have less energy, it's almost like they're lazy and they don't want to do it. You get what I mean? But how many electrons there are doesn't affect anything. And remember, how many electrons there are is linked to the brightness or the intensity of the light. Alright? Okay, let's move on. Let's now get on to Rutherford's model of the atom. Now, this was a very basic model of the atom. I think it was around 200 or 300 years ago. It definitely wasn't the worst. We've had less advanced ones. But there are some issues with it. So let's quickly go over its properties. And you need to make sure you know these because this is explicitly mentioned on the syllabus. So Rutherford's model of the atom is like the stereotypical one, the one you kind of see in diagrams, in like pop culture and stuff, like Big Bang Theory, that kind of thing. So it denotes an atom with mostly empty space, positively charged nucleus in the middle, and then the negatively charged electrons orbiting around in set predictable paths. So there were a few issues with Rutherford's model. All right. The first one was the stability of the atoms. So Rutherford's model kind of predicted that because the electrons could orbit at any level, that they would constantly be losing energy. All right? Because they're accelerating, their direction is changing, which means they're constantly emitting EMR. They're losing energy. All right? So that means that they're going to slow down. These electrons are going to slow down because they have less energy. And then because they have less energy, they're going to get closer and closer to the nucleus as they have less and less energy to overcome the attractive force between the nucleus and the electrons. And then the electrons will eventually collapse into the nucleus and the atom will not be stable. All right? So Rutherford's model really had issues with the stability, all right? Because what we see in everyday life is not that atoms are super unstable, but Rutherford's model predicted that they were super unstable, all right? So the other issues with Rutherford's model was that the electrons were located in the wrong place. So it doesn't give any mention of where the electrons are, which is addressed by the Bohr model, which we'll get into next. The other thing is the consequence of the atom instability is that Rutherford's model predicted, so this EMR that's being emitted as the electrons are moving around, he predicted that because the electrons have no set orbit, that they will be emitting all different frequencies of light, a complete spectrum of light, all right, all the different colors. And this isn't what we saw when experiments were done, and we saw that actually only certain frequencies, only certain colors of light were emitted, and this didn't match up with Rutherford's model. So we're now getting into the Bohr model, and the Bohr model addresses some of the issues with the Rutherford model. So Bohr said that electrons only radiate energy in exact quanta, or like definite amounts of energy. Only exact amounts. All right? So he also said that as the electrons radiate energy, they move inwards towards the nucleus in definite quantum orbitals. So the electrons are not just kind of moving about wherever they want, they are in definite orbitals, and they do not exist in between those orbitals, all right? And they keep moving down towards the nucleus until they've reached a stable orbit. So have a quick think about how this addresses the issues in the Rutherford model. All right? So firstly, if energy is only radiated in exact quanta, it means that only exact frequencies of light will be emitted, not a whole spectrum of light, as Rutherford's model predicted. So only a few different colors are going to be emitted, and this is exactly what we saw in experiments, right? What he means by definite quantum orbitals is that, I remember my physics teacher explained to me like a bookshelf, all right? If you have a bookshelf, the books cannot be in between shelves. All right, you've got to think about the electrons as if they're books and the shelves as if they're the quantum orbitals. All right, the electrons cannot exist in between the quantum orbitals. They have to be on the quantum orbitals. All right, okay. Now let's get on to emissions and absorptions. So, when an electron jumps down an orbital, it loses energy, which is equal to the difference in the energy states, all right? So say it has a certain amount of energy here. If it jumps down, all right, so it has 3 energy here and 2 energy here, it emits 1 energy. Got what I mean? So sometimes as well, an electron will absorb energy, all right? So sometimes it will absorb energy, say by a photon, and it will jump up a orbital state. Excuse me. So the energy that it absorbs will be directly equal to how much it jumps up in the orbitals, right? So let's get on to some evidence of the Bohr model. So as you can see here, I've shown you guys what a continuous spectrum looks like, all right, with all the colors. And then we have the emission lines and the absorption lines. So the emission lines show what frequency of light is being emitted, all right? And as you can see, it's only certain frequencies, and that's because in the Bohr model, the electrons are only orbiting at discrete orbitals, which means that when they emit energy, it's only discrete amounts of energy, all right? And the amount of energy of the light corresponds to the frequency and the color. So then obviously our emission and absorption lines are kind of opposites, right? So the light, or the frequency of light that a electron will absorb is opposite to that of what it will emit, which is really cool. All right? So let's move on now to Balmer series. So in 1885, Balmer determined the mathematical relationship between the light colors emitted by excited hydrogen atoms. And we have a formula describing that here. So we have 1 over the wavelength is equal to R outside of 1 on N final squared, take 1 on N initial squared. Alright? So we can use this formula to determine the wavelength here. So Bohr determined the orbits for the hydrogen atoms' electrons based on the wavelength for the spectral lines, giving the Balmer equation. Right? So this diagram is something you can definitely expect to see on your external exam. Alright, it does tend to come up quite a bit, so make sure that you're familiar with it. Alright, now let's get on to de Broglie's justification of the Bohr model. So, de Broglie applied the theory of wave-particle duality to the Bohr model of the atom, and basically what he showed is that the rotational velocity of the electron was quantized. Alright, I can't quite remember the exact term for it now, but he kind of showed that when an electron was spinning around, that velocity was quantized. Right? It only came in discrete amounts. It wasn't a continuous spectrum. So he determined the de Broglie formula. N times the wavelength is equal to 2 pi r. Alright, and that can also help you in determining your, in calculating your energy levels here. Alright, before we finish off, I'm just going to give you guys some quick study tips. So, firstly, make sure you do lots of practice questions and homework in exam conditions without constantly referring to the textbook, that kind of thing. Make sure you please practice difficult questions. That really is one of the most important things. Make sure you practice difficult questions. Make sure you kind of go through your textbook and see what difficult questions you can find, especially on electromagnetism, because there typically is a complex one on electromagnetism. Make sure you're always marking your work and picking up on any common mistakes that you make. Make a list of the common mistakes, and then make sure when you're practicing, when you're in exams, that you're constantly reminding yourself, hey, don't make those mistakes. I know something I'd always forget to do is like square C in those like E equals MC squared equations. I'd always forget to square C for some reason. That kind of thing, where it's just so simple, but you always kind of tend to make that mistake. Make sure you don't do that. Make sure when you're learning, refer to your formula sheet instead of the formulas you've written in your book. Refer to your formula sheet, because in your exam, you'll know where everything is. You won't be panicked. It will be familiar to you, that kind of thing. For learning concepts, make sure you're doing spaced retrieval. So you are going back to your notes every, after 2 days from you've learnt the content, after a week, after 2 weeks, that kind of thing. And you are asking yourself the questions, hey, what is this concept? And then explaining it to yourself without looking at the answer. Don't read over it first. Just try to remember it without looking at anything to begin with, right? Make sure you have variety in your notes, and then even past kind of like making nice notes, make sure that you practice a lot. I really cannot emphasize this enough. It doesn't matter how nice your notes are. I mean, I like making nice notes. I'm not being a hater on people who don't like nice notes. I love nice notes, but my point is practice really is the key. You really need to practice, all right? It's not just about constantly going through the textbook and rewriting your notes. No. You need to practice, okay? Moving on, make sure you take your mocks seriously if you haven't already done them. And then even if you feel like you didn't do as well as you wanted to, it's okay. I don't think I did particularly well in mocks either. Don't worry. Make sure you have a glossary or a definition bank. It's really important to use flashcards and that kind of thing. Make sure you use the QCEE definitions, not your textbook definitions, because the QCEE definitions are what they're going to use in your exam. Alright, so what you need to do is go to the QCEE syllabus, Control F the document, and memorize those definitions. Make sure you start practicing as soon as possible if you haven't already. You have a lot to remember. And then please also remember when you are remembering those define and explain syllabus dot points where you have like a concept, make sure you write a really concise definition in your own words, and then pop that on a flashcard and memorize that, because there's a lot of questions in an exam that'll just be like, explain the photoelectric effect, or explain Lenz's law, or something like that, and all you need to do is just like write it down. Like a really classic one is like explain how transformers work using Lenz's law and Faraday's law, or something along those lines. All right, so go through all those explain and describe dot points in your syllabus, Write down a short explanation. Don't plagiarize. Write it in your own words, and then practice it. All right, memorize it. So the other thing I have to remind you guys is to please, 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 please practice the questions. All right, practice difficult questions. Practice really is the heart of it. Practice throughout the year to the extent that you can. I know it's sometimes difficult if you have, especially in your externals, if English is coming up first, you just want to dedicate all your time to English. I know I've fallen into that trap, and I still do fall into that trap all the time. But regardless of what exams you have coming up first, make sure you just at least do a little bit each day or something like that, especially right in the lead up to externals. Another good helpful thing to do is to steal some friends, make a study group, make sure you can explain the concepts to other people or have other people explain the concepts to you that you're having trouble with. It really is helpful either way. If somebody's explaining something to you that you didn't know, you learned something. If you're explaining something to somebody that they didn't know, you're also practicing your explanations and you're deepening your understanding of the concepts and strengthening it. Because then when you get into an exam, and especially to do with those electromagnetism concepts, with all the right hand rules and like the lenses law and that kind of stuff, where you have to use a lot of conceptual rules and apply them to a lot of complex scenarios. Practicing those really, really, really helps, because then you can apply them to complex situations and contexts that you're not familiar with, right? Okay. Next, make sure you know how to use your calculator. That's really important too, especially for maths, I would say, where you're very much expected to use your graphics calculator. But make sure you know how to use your calculator, even if it's for those simple things like, solving quadratics and that kind of stuff, especially with projectile motion and things. Make sure you know how to do those on EQUA, or knowing how to use solve-n if you need it, or table, or any of that kind of stuff. Do some regular physics study, even if it's on the holidays. The key to this, though, is not to put an insane amount of pressure on yourself to do it. Alright, just relax. Doing study on the holidays can seem really arduous, but I promise if you do like 15 minutes a day or something like that, something really, really small, and then you do not put pressure on yourself at all to do any more than that or even to do well, just really have low expectations for yourself. Just be proud of yourself for whatever you do. It won't feel like a massive burden. Alright? And it'll just be kind of like a chore that you have to do every day, like making the bed or something. It's not like massive, it's just little. Alright? Make sure that you rest. Make sure that you look after yourself. That's really important. Make sure you're looking after yourself physically, as in drinking enough water, sleeping enough, eating enough, that kind of thing. Also make sure that you're looking after yourself mentally. That's really important too. Don't put too much pressure on yourself. Don't feel, I know it's hard to say being out of that situation, but try not to stress too much. Don't focus on it. If you constantly find yourself thinking, oh no, I'm going to fail, that kind of thing to yourself, stop it. Just stop thinking that, or try to minimize it at least. Every time you find yourself thinking something negative about it, try to think something positive instead. Alright? Be friends with your teacher if you can, or a different teacher if yours isn't A1. Anybody or even your friends who are really smart, be friends with them, older siblings, that kind of thing. They really are there to help you. Seek help and clarification if you're having trouble with anything. Don't feel embarrassed. Go and ask somebody. It'll almost be far easier to ask somebody than try to figure it out yourself. And I know that because I would never, I would refuse to ask for help with things, and it would waste a lot of time, quite honestly. And then break down the formula sheet without using your notes or looking anything up. So a really good thing to do, especially for those topics where there's a lot of different equations and they all have like different but kind of similar applications, all right? Especially electromagnetism, where all the equations look kind of a little bit similar, not gonna lie. Go through and be like, okay, well, this one is for a solenoid, this one is for a straight wire, this one is for, an electron moving or a proton moving by itself, and like this one is for this, and this one is for this, and go through and write it out and highlight it, and then do it without having anything written on the formula sheet or any notes, and go through, tell somebody else what it is, that kind of thing. And yeah, that is all of the study tips that I have for you guys today. Otherwise, I'm just going to go through a quick summary. So, what we went through today is special relativity. We went through Einstein's postulates, time dilation, length contraction, change in mass. We also went through mass-energy equivalence, and then Einstein's paradoxes. Then we went through quantum. We went through Young's double slit experiment, the black body radiation, the photoelectric effect, and then Rutherford and Bohr's model and the differences between them and their strengths and weaknesses. Alright, just a few reminders. Study consistently, don't stress. I know it's hard to put into practice, easier said than done, but really don't focus, don't put out negative energy. Do lots of practice questions, check your answers, please, and then make sure you do all the past exams on the QCEE website, or even go and do past exams from other states, other textbooks, that kind of thing. Alrighty. Thank you for listening. I hope this has been helpful, and have a great rest of your day.